everyone. Welcome to our next lecture series on windowing technique. So in Fourier series method, what basically happens is the infinite duration impulse response, which is represented by h suffix d of n, is truncated basically at n is equal to less than or equal to n minus 1 by 2. So this abrupt truncation of n from an infinite value into a finite value of n minus 1 by 2, this in turn results in finite duration sequence. So we will be able to obtain a finite duration sequence from an infinite duration sequence. So this abrupt truncation in turn results in some form of noise or unwanted oscillation in the frequency response curve. Okay, so in order to reduce such unwanted distortion or unwanted oscillation, basically this windowing technique is preferred. Okay, so the need to move on to windowing technique is basically to reduce this unwanted noise or disturbances or oscillation that basically occur in the frequency response. So this window sequence is represented by W of n. It is basically a finite duration sequence and it is mathematically represented by the formula W of n is equal to W of minus n. So FIR filter is basically symmetric. Therefore, W of n will be equivalent to W of minus n. This is not equal to 0 for this n value ranges from minus of n minus 1 by 2 to plus n minus 1 by 2. And the sequence value, the window sequence value will be equal to 0 for n value greater than n minus 1 by 2. Okay, so this is with respect to the window sequence. So to sum up, this windowing technique is basically used to form a finite duration sequence having with us as infinite duration sequence. How basically this happens? So h of n is the finite impulse response. So this finite impulse response is obtained by multiplying infinite impulse response, which is defined by h suffix d of n, with the windowing sequence w of n. So when we multiply an infinite duration sequence h suffix d of n with the window sequence for the range of mod n is less than or equal to n minus 1 by 2, we will be able to arrive with the finite duration sequence h of n. So moving on to the frequency response curve of windowing technique. So the frequency response curve is plotted against omega versus w of e power j omega, which is nothing but your window sequence. Okay, so if you look at the characteristics of the window, whichever window we take. So the characteristics of the window, the central lobe will have the maximum energy or it will have the highest energy, and the width of the central lobe should always be narrow. Okay, and moreover the side lobes, as we protrude, as the omega value protrude towards pi, the side lobe value will have lesser energy. So as it moves towards pi, the side lobes will have the least energy. So this is with respect to the characteristics of the sequence. Moving on to the design steps of the window sequence. The first step is basically from any given frequency response. So frequency response will be given to us, which is represented by h of e power j omega. So from the frequency response, we need to find the infinite impulse response, which is h suffix d of n. Okay, so it is represented mathematically by h suffix d of n is the infinite impulse response. This is obtained by, or it is given by, it is equivalent to 1 by 2 pi integral minus pi to plus pi frequency response, which is h suffix d of e power j omega into e power j omega n into d omega. Since this is an infinite impulse response, the range of n will always be from minus infinity to plus infinity. So after finding the infinite impulse response, we need to choose appropriate window w of n. But this is step number 2. Okay, so there are various windows available. So rectangular window is represented by w suffix r of n, and it is mathematically given by 1 for the value of n ranges from minus of n minus 1 by 2 to plus n minus 1 by 2, and its value is 0 for any other value of n. Arming window is represented mathematically by wh of n This is equal to 0.54 plus 0.46 cos 2 pi n by n minus 1 for n less than or equal to n minus 1 by 2. And the window sequence value is 0. Otherwise, Hanning window is given by W suffix h of n is equal to 0.5 plus 0.5 into cos of 2 pi n by n minus 1 for model n less than or equal to n minus 1 by 2, and the value of Hanning window sequence is 0 for all other values of n. Blackman's window is represented mathematically by W suffix b of n is equal to 0.42 plus 0.5 into cos of 2 pi n by n minus 1 plus 0.08 cos of 4 pi n by n minus 1 for modulus of n less than or equal to n minus 1 by 2. And the value of the window sequence is 0 for any other values of n. Finally, after choosing the appropriate window and obtaining the window coefficients, moving on to step number 3, we need to multiply the infinite impulse response value with the chosen window value in order to obtain the finite impulse response sequence. Hence, finite impulse response sequence h of n is given by the formula h of n is equal to h suffix d of n into w of n for mod n less than or equal to n minus 1 by 2. And the value of finite impulse response is 0 for any other values of n. So after finding out the finite impulse response sequence, we have to move forward to step number 4. Step number 4 is basically we need to arrive with the transfer function. So of the realizable filter. So the transfer function of the realizable filter h of z is represented mathematically as h of z is equal to z power minus of n minus 1 by 2 into h of 0. So h of 0 is nothing but impulse response, finite impulse response at n is equal to 0. These are filter coefficients plus summation n tends from 1 to n minus 1 by 2 h of n into z power n plus z power minus n. So this is with respect to the design procedure or the step-by-step procedure to solve or design any type of filter, being a low pass filter, high pass filter, band pass filter or band reject filter using any of these 4 windows. Okay, moving on to the advantages of windowing technique. So in order to design a filter using windowing technique, minimum number of computations are basically required to obtain the filter coefficient. So all the filter coefficients are obtained with minimum number of computations. So this is the first advantage. The second advantage is when we construct or draw the frequency response curve, we could find there are no ripples present in the frequency response curve. So this is with respect to the advantages of windowing technique when compared to that of Fourier series method. So in Fourier series method, as we saw, as we protrude towards the side lobe, we would find more amount of ripples available in the frequency response curve. So that is eliminated using windowing technique. H suffix d of n is 1 by n pi sine n pi minus sine n pi by 4. So if you substitute n is equal to 0, sine 0 by n is equal to 0, you will have 0. So sine 0 by 0 is indeterminate form, minus 0 by 0 is indeterminate form. So if you substitute n is equal to 0 directly, so we will arrive with indeterminate form. So we need to apply L'Hospital rule here. So according to L'Hospital rule, we know that limit theta tends to 0, sine theta by theta is equal to 1. So this is the formula for L'Hospital rule. Upon applying L'Hospital rule here, so we break up the term into 2 terms here. So for the first term, we have sine n pi by n pi. So we are substituting the limit here. So limit n tends to 0, sine n pi by n pi minus, for the second term again, we substitute the limit separately. So limit n tends to 0, sine n pi by 4 by n pi. Now, if you could see here, According to this, limit theta tends to 0, sine theta by theta is 1. Okay. So that is satisfied for the first term. This condition is satisfied in the first term. So according to the first term, we have limit n tends to 0, sine theta by theta. Okay. Theta tends to 0, sine theta by theta. Here the theta value is n pi. Okay. So according to L'Hospital rule, for the first term, the value that we arrive with is 1 minus. For the second term, if you could see here, it is limit n tends to 0. We have sine n pi by 4 divided by n pi. In order to equate this to be 1, so whatever term we have in the numerator, theta value that we have in the numerator, the same theta value should be available in the denominator term also. Okay, the theta value in the numerator is n pi by 4. In the denominator also, we are supposed to have n pi by 4. In order to arrive that, so what we are doing it is, I am multiplying the numerator term and the denominator term with 1 by 4. So if we do so, according to L'Hospital rule, we have limit theta tends to 0, sine theta by theta is 1. So this complete term will become 1. Okay, therefore the resulting value is 1 by 4. So that is how for n is equal to 0, h of 0 is given by, for n is equal to 0, h of 0 is given by limit theta tends to 0, sine theta by theta is 1. Therefore 1 here minus 1 by 4 into limit theta tends to 0, sine theta by theta is 1 according to L'Hospital rule. Therefore, it is 1 minus 1 by 4. Hence, the answer that we have arrived here is 3 by 4. 3 by 4 is 0.75. This is for n is equal to 0. Similarly, for n is equal to 1. For n is equal to 1, in the impulse response, we need to substitute n is equal to 1. So, what is our impulse response formula? So what is our formula? So impulse response is given by, I'm writing it here for easy understanding and reference. So h of x d of n is what? Sine n pi minus sine n pi by 4 divided by n pi. So this is the formula. This is the value which we had arrived in the previous step. So in this, we need to equate n is equal to 1 in order to arrive h of 1. So h of 1 is equal to h of minus 1. This is equal to sine n. We need to equate it to be 1. So sine pi minus, here again n we need to equate it to 1. So sine pi by 4 divided by, in the denominator, if I equate n to be 1, I will have pi. So if we simplify this, the value that we arrive here will be equal to minus 0.225. Similarly, for n is equal to 0, in this equation or in this expression, we need to substitute n is equal to 2 correspondingly. So we arrive sine 2 pi minus sine pi by 2 divided by 2 pi. So this is equivalent to minus 0.159. Similarly, for n is equal to 3, we have sine 3 pi minus sine 3 pi by 2 divided by 3 pi. This is equivalent to minus 0.075. For n is equal to 4, h of 4 is given by sine 4 pi minus sine pi divided by 4 pi. This is in turn equivalent to 0. The last value is h of 5. So h of 5 is equivalent to, by substituting n is equal to 5, we arrive with sine 5 pi minus sine 5 pi by 4 divided by 5 pi. So this is equivalent to 0.045. Okay. So we had calculated the filter coefficients of finite duration sequence. Our next step is, we are expected to solve this problem using Hanning window. We know the window sequence for Hanning window is mathematically represented by WHN of n is equal to 0.5 plus 0.5 into cos of 2 pi n by n minus 1 for mod n less than or equal to n minus 1 by 2, and the value of the window sequence is 0 otherwise. Okay, so here the sample is 11. When you truncate it to be 11, the value of the window sequence, n value will range from minus 5 to plus 5. In a similar manner, we need to substitute, or we need to find out the filter coefficient starting from n is equal to 0 to 5. So w suffix hn of 0. So we need to put n is equal to 0 here. So this is equivalent to 0.5 plus 0.5 cos n is equal to 0. Cos 0 is 1. Therefore, it is 0.5. This is equal to 1. Similarly, to find out the filter coefficient at n is equal to 1, in this equation, I need to replace this small n to be 1. So it is 0.5 plus 0.5 into cos pi by 5. This is equal to 0.9045. Similarly, we are arriving with a value till n is equal to 5 and w suffix hn of 5 is equated to 11 is equal to 0. So we have found the value of the window coefficient. So our next step is we need to find out the finite duration sequence. So finite duration sequence is obtained by multiplying the filter coefficients which we had arrived for infinite duration sequence with the window sequence for n ranges from -5 to +5. So h of 0 will be equal to whatever value we had calculated in step number 2. We had calculated the filter coefficient of infinite duration sequence, and in step number 3 we had calculated the values filter coefficient of window sequence. So for subsequent value of n, if we multiply the filter coefficient and the window coefficient, we will arrive with the filter coefficients of finite duration sequence starting from n is equal to 0 to 5. Step number 5 is finally to find out the transfer function, which is h of z. So transfer function is given by h of z is equal to h of 0 plus summation n tends from 1 to 5 h of n into z power n plus z power minus n. So substituting the value of the filter coefficients, whatever we had arrived here, h of 0 is 0.75 plus this we need to expand. So this will be h of 1 into z power 1 plus z power minus 1. So h of 1 value is minus 0.204. So I have substituted h of 1 value here plus h of 2 is minus 0.104. So minus 0.104 into z power 2 plus z power minus 2 plus h of 3 value is minus 0.026. So we have minus 0.026 into z power 3 plus z power minus 3. H of 4 value and h of 5 value is 0. So it is not written in here. So we had arrived with the transfer function. The transfer function, whatever we have arrived so far, is not physically realizable. In order to arrive with the realizable transfer function, h dash of z is calculated, which h dash of z is given by z power minus of n minus 1 by 2. So capital N is 11. So 11 minus 1 by 2 is 5. Therefore, we have h dash of z is equal to z power minus 5 into h of z. So we had designed an high pass filter. Yes, so we had designed an high pass filter using Hamming window. The same problem could be solved using Hamming window. So in order to solve the same problem using Hamming window, step number 1 is retained. So where we find out the infinite impulse response sequence and we find the filter coefficient of infinite impulse response sequence. This is again the same. The only change is change the window sequence according to the question. So in this question, they have asked us to solve for Hamming window. We know that the window sequence that we obtained for Hamming window is w suffix hn of n. And it is given mathematically by 0.54 plus 0.46 into cos 2 pi n by n minus 1 for n ranges from minus of n minus 1 by 2 to plus n minus 1 by 2 and it is 0 otherwise. Since we have 11 samples, the value of n will range from minus 5 to plus 5. Substituting value of n is equal to 0 to 5, we can arrive with the value of the window sequences here. Okay, so WHN of 0 was found to be 1. WHN of 1 was found to be 0.912. WHN of 2 is found to be 0.682. WHN of 3 is 0.398. WHN of 4 is 0.1678 and WHN of 5 is 0.08. So we had obtained the window coefficients. So So after obtaining the window coefficient, the further procedure is the same. We need to find the filter coefficient, the finite duration sequence, which is nothing but the product of the filter coefficient of infinite duration sequence with the window sequence obtained. And accordingly, the filter coefficients of finite duration is formed as explained earlier. Then moving on to step number 5, finding out the transfer function of the filter, which is given by h of z is equal to h of 0 plus summation n tends from 1 to 5 h of n into z power n plus z power minus n. Substituting the values of the filter coefficient, we arrive with the final value here. And finally, the transfer function of the realizable filter is given by h dash of z. This is equal to z power minus 5 into h of z. So by this, we can solve or we can design a filter using any of the window available. Okay, hope you like the session. Thank you.